What's going on, YouTube? It's your boy Lonnie Reaction. We are back with another reaction video. Now, I just came across this very interesting video. Sagittarius A might not be a black hole. What? Now, for those of you who don't know, Sagittarius A is like that supermassive black hole. I think in the center of our galaxy, I believe. Yeah, it's like at the center of our galaxy. But it's interesting. It might not be a black hole. What is he talking about? But because I do know, like, NASA and scientists in general, they come out with new theories like every single year, bro. But I've never heard of this one. Sagittarius A might not be a black hole. I'm really wondering why. What makes scientists think this? Because I've never heard otherwise. But honestly, I don't got too much to say. Let's just dive into this, man. So now, why Sagittarius A might not be a black hole?
At the center of the Milky Way lies a dark beast, millions of times more massive than the Sun. And everything in our galaxy rotates around it in a gentle dance. This is Sagittarius A star. For decades, astronomers have tracked the orbits of its closest stars, and every observation has pointed towards the same conclusion. It is almost certainly a supermassive black hole. But even with the publication of the iconic image that came from the Event Horizon Telescope in 2022, it's important to remember that this hasn't yet been proven. And now, fresh research is rewriting this familiar story.
There's one thing with like space in general. A lot of this shit isn't proven, bro. It's just our theories. Like they mathematically make sense, but we don't actually know. And it's actually really interesting. This is why I've always been so fascinated with space, with the universe, because like, bro, we just don't know. We don't, and it's just so interesting.
Sagittarius A star may not be a black hole at all, but a compact core of dark matter. One that spreads through and beyond the galaxy into a vast spherical halo. This model not only challenges the consensus on the nature of Sagittarius A star, but also tackles one of the biggest unanswered questions out there. What is dark matter? Perhaps it's been at the very heart of our galaxy all along. I'm Alex McColgan and you're watching Astrum. Join me as we explore a radical take on Sagittarius A star, which could overturn everything we thought we knew about the very core of our galaxy. A theory that suggests it's a different beast entirely, and that it connects and could even solve two of the biggest mysteries in modern physics. Around 27,000 light years from Earth, in the very center of our galaxy, is Sagittarius A star, a massive and extremely compact object shrouded in dense clouds of interstellar dust that, by its very nature, we cannot observe directly. The first clues of its existence were found in the 1930s, when Karl Jansky detected an unusual radio signal coming from the direction of the Sagittarius constellation. At the time, no one knew what it was. Black holes were still considered mere mathematical curiosities, and hypotheses about what it might be buzzed around the scientific community. Could it be clouds of star clusters, or perhaps remnants from a supernova? It wasn't until 1974 that it was identified as a single compact object by Bruce Ballack and Robert L. Brown. Brown later named it Sagittarius A star. The theoretical groundwork for the existence of black holes had been laid in the intervening decades, and it didn't take long before two and two were put together and speculation grew that Sagittarius A star was likely one of gargantuan size. As observations improved in the 1990s, astronomers were able to see stars orbiting an apparently empty region of space at astonishing speeds. Since those stars must be under the influence of something millions of times the mass of our own sun, they became the strongest evidence we have for a supermassive black hole. The path of these stars, termed S-stars, became remarkably well mapped. They are the closest known stars to Sagittarius A star and move at speeds of up to 24,000 kilometers a second, which is around 8% the speed of light. One of them, S2, completes a full orbit in just under 16 years. For context, our sun takes more than
Ooh.
200 million years to complete its orbit of the
That's
galaxy.
fast.
By tracking the orbital motion of these S-stars, astronomers can calculate the size of whatever it is that is sitting at the heart of the Milky Way. In fact, the researchers who did this won the Nobel Prize in Physics in 2020.
Hey.
Just like many modern-day astronomical endeavors, this discovery was a truly international effort. Scientists from all over the world made up the teams who did these calculations, and to do so would have required them to communicate despite their differing native languages.
Sponsor.
And that's where today's sponsor, Babel, comes in. It's this year worth a try.
Gensel at the Max Planck Institute teams, led by Reinhard Gensel at the Max Planck Institute and Andrea Ghez at UCLA, found that Sagittarius A star has a mass of around 4.3 million suns, and it's confined to a region only 23.5 to 25 million kilometers across, which is small enough to fit within the orbit of Venus. Their Nobel Prize was shared with Roger Penrose, who provided the mathematical proof that black holes are a direct consequence of Albert Einstein's theory of relativity. It seemed that Sagittarius A star's status as a supermassive black hole was cemented. But detail here is important, and the official citation on Gensel and Gez's Nobel Prize reads, "For the discovery of a supermassive compact object at the center of our galaxy." And
Not
whilst the
black hole.
consensus is that Sagittarius A star is a supermassive
It's not
black
proven.
hole, it has not actually been proven, and scientists are still testing alternative ideas. In fact, it's never been the only possible explanation, and other theories have been around since the first detection of Sagittarius A star's radio signal. But the discourse moved to the fringes as other possibilities, such as a star cluster, were eliminated as the S-star data built over the decades. But some ideas remain.
Gotta pause it. This is so beautiful. Like, I'm wondering, like, if you were to actually float in space, is this what you'd see? Probably not. You'd probably, like, the stars would be extremely far apart. Like, but that's such a beautiful picture.
Including boson-star models, which propose that Sagittarius A consists of bosonic particles, gravastars, dark matter cores surrounded by a shell of high-energy matter, and compact cores, which are made entirely of dark matter.
To understand why these ideas have persevered in the literature,
We need to consider what we don't know about Sagittarius A star. And it's here we find one of the greatest unsolved problems in astrophysics. How do supermassive black holes form? Well, here's the simple truth. We don't know.
But we do have
Stellar
theories.
and intermediate mass black holes, which range from a few times the mass of our Sun up to 100,000 solar masses,
Oh my god.
form when a massive star uses up its nuclear fuel and collapses in on itself. Under certain conditions, including the starting mass of the star relative to the remaining core, these violent deaths leave behind a black hole. This process is very well understood, and the signatures of these black holes are well observed. Some astronomers estimate that there may be as many as 1 billion stellar black holes in the Milky Way
Oh my
alone.
god.
But Sagittarius A star is a completely different category. At 4.3 million solar masses, it is far too large to have formed from the collapse of any known star. There simply are no stars massive enough to collapse and form a black hole of this scale.
Well, unless it happened maybe millions of years ago and over time it's just grown larger. I don't know though.
What's more, by definition, we cannot observe black holes directly. They do not emit light, and photons that cross the event horizon become trapped. Their existence is only inferred by the effects
Surroundings,
they have in their
that
surroundings.
they like warp
And
space.
this leaves the door ajar for alternative theories, and an elegant one hit the headlines in February 2026. Valentina Crespi at the Institute of Astrophysics La Plata in Buenos Aires studies dark matter at galactic scales. She and her collaborators statistically compared an alternative black hole model, one where Sagittarius A star is composed of a dense, dark matter core, to the observational data of S2 and 5 known G objects. G objects are a unique class of objects discovered in the early 2000s. They behave like stars, but look like gas, visibly changing shape as they move closer to Sagittarius A star, distorting under the influence of its intense gravity. It's thought they could be compact dust clouds, or stars cloaked in a thick shroud of gas and dust. This strange, shifting morphology would need to be replicated by any models challenging the supermassive black hole consensus, and that's exactly what Crespi set out to do. Her aim was to determine whether a dark matter core could reproduce the behavior of S2 and the G objects to the same level of precision as the black hole model. Published in the monthly notices of the Royal Astronomical Society in February 2026, the results were remarkable. A dense core of dark matter in this model could reproduce the orbits, with less than 1% difference to the black hole model. What this means is that you cannot tell the difference between a dark matter core and a black hole with the observational data tested. Both have the same gravitational effects on S2 and the G objects. Even more remarkable is that this model has implications far beyond the nature of Sagittarius A star. Crespi and her international collaborators propose that it solves another huge mystery in physics: what dark matter is made of.
Now, this is something I really want to know, because, like, bro, when I first got into, like, science in general, space in general, bro, and just learning about dark matter, what the hell? Like, because what? Dark matter? You telling me 95% of our universe is made up of some shit we don't even know, we can't see? Like, it's insane.
To understand how significant this is, we first need to take a small detour and unpack what we currently know about dark matter. I'll cover it in summary here, but for a deeper dive, please check out my other video about the recent possible observation of dark matter. Dark matter was first proposed by Fritz Zwicky in the 1930s,
I remember learning about him.
after he observed that galaxies in the Coma cluster were moving too fast for known physics to explain. With relative speeds of more than 2,000 kilometers a second, these galaxies should have flung themselves apart.
And shout out to Frisky. Sorry for pausing, but I remember when I first learned about him and learning that he basically passed away. He passed away not knowing just how important his discovery was. It's just really sad. That happens a lot too.
If the gravity holding them together was proportional to the matter he could see, something else was adding mass to the system, and he termed it dark matter. Later observations saw something similar in the rotation of galaxies. Stars in their outer regions orbit at speeds that cannot be explained by visible mass alone. Dark matter must be providing the extra mass to maintain these velocities, and it turns out it permeates the known universe. Closer to home, it is thought that the Milky Way is surrounded by a dark matter halo, a vast and diffuse sphere stretching far beyond the visible disk of stars and gas. So, in a situation not dissimilar to the one I described earlier, we know dark matter exists through the gravitational effects it has, and current models suggest that dark matter makes up about 85% of the matter in the universe.
Dark energy, like dark energy. It's just insane, bro. And like, what's more interesting to me is the fact that what if like space in general isn't just black? What if that's just because our eyes are, what if that's just because our eyes are designed to see something? Like, what if there's not actually what's there? It's something entirely different. Like, I don't know how to explain this. Some of you might know what I mean, but like, bro, what if at night when you look at the sky, that's not what's actually there? It's just our eyes telling us that's what's there. It's something I've always thought about.
But we don't know what it's made of. It doesn't emit, reflect, or absorb light in any known way, and it has not yet been directly detected. There are a number of candidates in the race to identify dark matter, with
axions and WIMPs the most widely studied. An intriguing paper published in November 2025 may have found a telltale annihilation signal associated with WIMPs in historic data from the Fermi telescope, but snags remain and the dark matter question is still open. And this is where the team at La Plata comes back in. They propose that dark matter consists of dark fermions, a candidate that is not expected to produce any detectable signals at all. It's an idea that was first put forward by astrophysicists Ruffini and Bonazzola in 1969, and it's been fizzling in the background ever since. Fermions are subatomic particles, including electrons and quarks, with half-integer spin and are basic building blocks of matter. Of crucial importance for us is that they obey the Pauli exclusion principle. No two identical fermions can occupy the same quantum state. In other words, they cannot be in the exact same location in space with the same energy and the same spin at the same time. This is a fundamental rule of quantum mechanics.
Bro, it feels like I'm back in chemistry class because I remember learning all of this shit. Like, I remember my teacher, Mr. Coulter, I don't know if you're watching this. I remember, bro, he used to go over this shit, bro, like literally. And it's all just coming back to me.
The reason why matter doesn't collapse in on itself and why we can't walk through solid walls. This is a property they share with the proposed dark fermions. They are posited to be elementary particles too, but they only interact with the rest of the universe gravitationally, not electromagnetically, making them dark. Because of the Pauli exclusion principle, dark fermions cannot be infinitely squeezed together. They push back and resist collapse, so they could coalesce and, under the right conditions, build up huge amounts of internal pressure. This results in an ultra-dense, stable object which, in theory, could reach masses similar to a supermassive black hole. Proponents of this model, including the group leader at La Plata, Dr. Carlos Arguelles, suggest that a core of fermionic dark matter would be so dense that it would, in every observable sense, be indistinguishable from a supermassive black hole. But unlike black holes, such cores would not form a singularity, nor have an event horizon. And that's not all. Fermionic dark matter would extend beyond a compact core, naturally forming a distinctive structure that diffused through the galaxy and beyond to form a halo. Put most simply, it's proposed that Sagittarius A star and the dark matter halo are not two separate objects. They are two parts of the same continuous structure made from fermionic dark matter. This is something no other Sagittarius A star hypothesis does. In every other scenario, the compact object and the dark matter halo are two distinct structures. This is the only theory that unifies what we see in the galactic center with the hypothesized dark matter structure of the galaxy. It's incredibly elegant and rather convincing, I personally think.
It is, I'm not gonna lie.
Now, as we've seen, one of the key pieces of evidence for dark matter's existence is how galaxies and the stars within them rotate. Something is adding mass and influencing their speed. ESA's Gaia mission is bringing extraordinary detail to this picture. Its aim is to accurately measure the motion of 1 billion stars as they orbit the center of the galaxy, from its inner regions to the outer disk. And the published data in 2022 brought an intriguing twist to this tale, with particular importance to the fermionic dark matter model. Gaia revealed something totally unexpected at the outer edges of the galaxy. A slowdown in the rotation of its outer arms, called Keplerian decline. This presented a problem for the standard picture of our galaxy. Most dark matter models cannot reproduce this observation. But fermionic dark matter, thanks to our old friend the Pauli exclusion principle, could form a dark matter halo that is a clearly defined sphere. It would have a sharper boundary than other dark matter candidates,
and this would naturally lead to the drop-off in speed observed by Gaia. In other words, Gaia is not just mapping stars, it's tracing the distribution of gravity across the Milky Way. There are other observations that can show us gravity's effects in our galaxy, and the most well-known takes us back to where it is strongest, the extreme environment around Sagittarius A star. This enigmatic image from the Event Horizon Telescope, published in 2022, was widely described as the first direct image of our black hole shadow. Again, the devil is in the detail here. What the EHT image shows is glowing hot matter circling Sagittarius A star, bent into a ring by the object's extreme gravity, which is consistent with a black hole. We're also seeing a shadow against the surrounding glowing gas. In a 2024 publication, Arguelles and his team demonstrated that a dense fermionic dark matter core could mimic this shadow because its extreme gravity would bend light just as strongly, producing an image almost indistinguishable from the black hole scenario with current instrumentation. As Crespi describes it, our model not only explains the orbits of stars and the galaxy's rotation, but it is also consistent with the famous black hole shadow image. The dense dark matter core can mimic the shadow because it bends light so strongly, creating a central darkness surrounded by a bright ring. And if it turns out to be true, this theory comes with some other exciting implications. Thanks to the James Webb Space Telescope, astronomers are able to peer deep into the past, imaging galaxies whose light has taken so long to reach us that we're seeing them as they existed less than 1 billion years after the Big Bang. Something interesting has been found in the center of some of these galaxies, called little red dots. These are thought to be compact masses hundreds of millions or even billions of solar masses in size. And it's very difficult to explain what they are. How could something so large form in such a short timescale? Since their discovery a few years ago, there have been hundreds of papers and almost as many theories that attempt to explain them. Fermionic dark matter cores fit remarkably well here too, because they could be established far earlier in the history of the universe than a supermassive black hole. In the dense conditions of the early universe, fermionic dark matter would have been able to clump together to form compact configurations without needing any other starting points such as stars at all, which would explain why we can see extremely massive objects so early in the historical cosmic record. But before I get too far ahead of myself, let's take stock for a moment. We have S-star and G object orbits, the Gaia rotation curve, and the EHT shadow. A fermionic dark matter model can reproduce these current observations with striking accuracy. But as the teams are quick to point out themselves, their theory is not proven, and their work has not shown the black hole model to be wrong or shifted the consensus view. It is still considered most likely that Sagittarius A star is a supermassive black hole. But what Crespi, Arguelles, and their collaborators have done is shown that a fermionic dark matter model cannot be ruled out by current data, and it deserves a closer look. And beyond our current abilities to detect, there is a signature unique to black holes that could help settle the matter. Around a true black hole, the intense gravity near the event horizon can force photons to spiral multiple times before they disappear beyond it, never to emerge again. This phenomenon, called photon rings, would not exist around a dark matter core because dark fermions would resist being squeezed into a singularity in the first place. The dark matter core remains a stable, dense sphere rather than a bottomless pit. Without the event horizon, light is simply bent by the core's gravity and flies away, rather than getting trapped in the endless loops that create a photon ring. Imaging such a structure around Sagittarius A star is actively being worked towards. NASA's Black Hole Explorer mission aims to launch a new space-based radio telescope, which would link directly to the next generation EHT. Such an endeavor would create a virtual telescope larger than Earth, but it could be decades before this comes to fruition. In the meantime, the Gravity Interferometer at the VLTI in Chile is being continuously developed. This interferometer is already tracking the pericenter precession of S2's orbit, measuring the subtle changes in its orbital path with each loop around Sagittarius A star. The direction of this shift, and by how much, could provide further constraints for competing models to be tested against. At the other end of the scale, direct detection experiments like the NEON experiment in South Korea are beginning to hunt for dark fermions. Researchers are looking for the minute traces of energy resulting from a collision between a passing particle and an electron. If signals like this are detected, they could offer vital clues about the properties of dark matter and help us understand what it's made of. What I find so fascinating about the fermionic dark matter hypothesis is its elegance. For decades, two of the deepest mysteries in physics have been treated as entirely unrelated: the nature of the supermassive object at the heart of the Milky Way, and the nature of dark matter that makes up most of the universe. The La Plata team and their international collaborators propose that these problems are one and the same, and it's compelling. If they are correct, it would change our understanding of Sagittarius A star and the universe itself. It's a bold claim, and the consensus still points overwhelmingly towards a supermassive black hole, but both are far from proven, reminding us that some of the most fundamental questions remain open, even at the center of our own galaxy.
Patreon members got access to this video and
This was a really good video, a mind-boggling video. Because like I said in the beginning, bro, we don't know shit, bro. It's all theories, bro. It's all hypotheses. It's so interesting. But I actually do like that theory that maybe Sagittarius A is ferment dark matter. Yeah, you know what he said. Cause it was very convincing. Like it was very convincing. But excuse me, I'm sorry. It was very convincing. And as I said, bro, we don't know shit. And this is why I love just science in general, bro, because it's so much you can learn. Like, I just learned so much stuff in this 26-minute video. I was already pretty knowledgeable, but again, I just learned so much. Like those little red dots. I didn't know I'd never heard of that. This video was amazing. And yeah, I gotta subscribe to Astrum. I do believe I've watched one of his videos before, but never actually like reacted on this account. But yeah, if you like this video, please like and subscribe so I can continue giving you guys these reactions, and I'll see you next time.